Alright, so welcome back to particle physics and the Standard Model. This is lecture 54, and in the last class we were finishing up on some aspects of decays, and in particular we had moved on from short lived particles to long lived particles. Okay. By long lived we mean really long lived, longer than human time scales. Then how do you measure the lifetime of the particle? You do not really wait along, you assemble a large number of these particles and measure the population as a function of time, right. And one prototypical example of that is proton decay, and we saw that from the fact that we do not administer a lethal dose of radiation to our cells, we can measure, we can actually set a limit on the lifetime of the proton. And we saw that was about 10 power 18 years, which is already 8 orders of magnitude larger than the lifetime of the universe. And in practice what people do is to set up tanks of water or other liquids and look for the decays of protons. And in particular the super Kamiokande experiment, which has set some of the best limits in this business, have used about 20 kilotons of water, and they waited on time scales of a year, and all that put together gives you the lifetime of the proton to be at least 10 power 34 years. That is the experimental limit. Okay. Now compare all that with the Standard Model theoretical limit. Standard Model theoretical prediction is about 10 power 137 years. So we are still way short of that, but that is not the point. The point is to see if there is something beyond the Standard Model that can make protons decay faster. Okay. And we ended by starting to see the connection between the number of dimensions, number of time dimensions and particle decays. And for that we started with this little space time diagram, where I showed that if you take a time like vector and bent it in time like directions actually, right, then even though I am going in the time like direction, all the bends are in space like directions, all the distortions are in space like directions, so that in the metric or in the interval, in this case dx square is now larger. That would mean even though I've bent it around, that's actually a shorter route in the space time diagram. Okay. Now let's take this further. Alright. Suppose I bend the green line in this direction. Okay. What about that? Is that longer or shorter? Again think about it, pause your video to think about this, but I am going to give the answer now. No surprise that it is also actually shorter. Why? Because those distortions are also in space like directions, right. Those arrows are literally perpendicular to the green line again, and that is also in the space like region, right. So what is the grand conclusion of that bit? It is that time like vectors are maximal. That is, there is no route that you can take in the space time diagram other than the straight line route that would be longer. Okay. That is the longest route you can take is the straight line on this plane in Minkowski space. Okay. Now I am going to draw one more space time diagram. Once again let me draw the null vectors. So here these are okay. We have this time a space like vector, okay. and I am going to do the same thing again. I am going to bend it first in the time like direction, alright, and I am going to ask the same question: is the red vector longer or shorter than the green vector? Now this time it is better to write the interval in this way, right, to keep it positive, dx square minus dt square. Okay, and think about it again. Again, pause your video if you want and think about whether this is longer or shorter. See, it's the same logic as before. Okay, what have I done here? I am just bending it such that, you know, there is a series of bends in the time like direction, right? What does that mean? That is just parallel to, all these arrows are parallel to this arrow which is perpendicular to the green line, which is in the time like region, right? So it is the same old logic again, right? So what have I done? I have just increased this has become larger, and that means the red line is shorter. Once again, same thing, right? Similarly, over here, is this red line shorter or longer? Again, it is the same thing. I am not changing anything here compared to the previous arguments, right? Once again, what is that arrow is right here. This is also time like. So once again, dt square is larger. So this is also shorter than the green line. Okay. But now I am going to ask, and this is the key here: is there any way in which I can bend that green line so that it is longer? Pause your video, think about this carefully. Think about what I have written as the title of this discussion and think about it carefully, okay? And the answer is that you have to think outside the page. I have drawn a space-time diagram on 2 dimensions, okay, with just one space dimension and one time dimension. But of course, in real life, we have 3 space dimensions, correct? In other words, I can bend the green vector out of this page, right, out of the board. So I can't draw it, that is why I have to write it actually. Agreed? Now that bend, yeah, will that be in the time like direction or the space like direction? Of course, that will be in the space like direction, right? That is the difference now. A time like vector can only be bent in space like directions. That is just what we saw here, right? This and this. And similarly, a space like vector could be bent in the time like direction, sure, but of course you have other space dimensions to work with. So it could be bent in space like directions also actually, okay. Or said differently, space like vectors okay are not maximal. They are neither minimal nor maximal. Just means if I bend it in the time like direction, they get shorter. If I bend it in the space like direction, they get longer, okay. So that is what makes time like vectors really special. They are already maximal. There is nothing else you can do. Even if you bend it in the space like directions, you know, I mean, you can only bend it in space like directions, basically all 3 directions, okay. Now what does all this have to do with particle decay? It goes like this, okay. Now instead of time and position, I am going to draw energy and 3 momentum, okay, and in particular let us call this px or something, okay. So, I will just call it px, alright, or you know what, I will just retain this. You have to understand that we are talking about some component of the momentum, okay. This could generally stand for any component, okay. And let me draw the null vector here, okay. And then I am going to draw the vector for a real particle, a time like state, okay. So, what is the length of that vector? The length should be e square minus p square under square root, right. So, what is that? That is nothing but the mass of the particle, the invariant mass, correct. So, okay. Now, if I had a particle A, okay, decaying to some B plus C plus D, right, I know that PA equals PB plus PC plus PD. These are all 4 momenta, right. This is literally energy momentum conservation or 4 momentum conservation, right. Now, I can represent that with simple vector addition, right. The vector addition rules that we saw for Euclidean space apply for Minkowski space also actually, okay. You can easily go work that out, okay. Said differently, I can if the energies and momenta of B and C and D were such that they can be represented on the space time diagram, I can just maybe I should draw this in red. So, I have this and this, okay. So, what is this? This is basically for the A particle and these are the 4 vectors for the 4 momenta of the B particle, C particle and D particle, okay. This is literally what I have drawn here is energy momentum conservation. So, 4 momentum conservation, okay. And we are almost to at the end of this discussion, because all I am going to say now is we already know from this discussion before that time like vectors are maximal, correct. The same thing applies here. This is a time like vector. So, this going from the origin to this point with a straight line is always going to be the longer route than going through a roundabout line like this, right, going for from here to here, from here to here and here to here. That is exactly what we have drawn here. Here we have done a distortion like as though making it look like it is a continuous distortion, but even continuous distortions can be thought of as sums of discrete distortions, right. So, here I am writing 3 discrete distortions. So, in other words, because time like vectors are maximal, it's worth writing it down. That implies that the mass of M, because that is the length of that vector, should be larger than or equal to mass of B plus mass of C plus mass of D, okay. This is why the mother is always heavier than the sum of the masses of the daughters in decay, okay. So, this is why you always have this. The fact that we have only one time dimension, okay, one time dimension plus more than one this case actually 3, right, space dimensions is exactly what leads to this. If we had had more than one dimension for time, right, if there had been 2 dimensions of time, this would not have been true. Lighter mothers could decay to heavier daughters, that could have happened. Okay, and then we might get tachyons and all sorts of weird things. Thankfully, we don't live in such a world. Keeping track of these things is hard enough already, and this is one particularly nice thing about our world. Okay. Okay, so think about this again. I think it's a very important thing to remember, this relation between relativity, 4 vectors, Minkowski space, and 4 momenta and particle decays. Okay, that ends what I wanted to say about decays. So let's now move on to more scattering, and in particular we will take up one quintessential problem, one quintessential example of scattering, which will help illustrate some very interesting things about the weak force. Okay, and I am going to call this section scattering without QFT. Without really making use of QFT, we can calculate a scattering cross section. Let us see how. Okay, and I am going to be dealing with an example that is dealt with in many textbooks, E plus E minus going to mu plus mu minus, okay, for which I have only one diagram to think about, namely this Feynman diagram. So, E plus in mu minus and mu plus, okay, and I am going to give some extra labels. I am going to call this particle 1, particle 2. This is just momentum labels if you want, 3 and 4, and of course this is the photon. Okay. So what I am doing here is I am thinking of the center of momentum energy smaller than the Z boson mass. Okay. Why? So that the Z boson exchange is not important. Okay. Now I could have also dealt with, let me just write it on the side. I could have dealt with E plus E minus going to E plus E minus, but then there will be more than one diagram for that, or I could have done this for QQ bar going to E plus E minus, or QQ bar going to QQ bar in QED, not in QCD, and so on. Okay, but I am not going to do all this because the main thing is what I am putting here, what I am putting in here is very high kinetic energies for these particles, so that the particles themselves, right, initial and final states, are massless. They are not really massless, but we can treat them as massless in this problem. Compared to the energies and momenta that we are going to put in, they are massless. Okay, that is the main point here. Okay. So, remember to calculate a cross section, there is really only one ingredient that we need to calculate, the rest of it is in d ellipse and the energy and all that, right. So, it is worth looking at the expression one more time. Here you go, in the center of momentum frame for instance, you have the amplitude squared, that is what you need to actually calculate, right. The other things are just there in the expression. So, if you look at the more general expression also, d ellipse you can compute, the energies are specified by the problem, right, V1 and V2 you would know, So it just comes down to m square. Okay. So that means let us compute the amplitude for this process, and to make life a little simpler, I am just going to pull out the coupling constant squared. See, this comes with a little E here and an E here, right? That is just the coupling constant of QED. This E is not the electron, this E is not charge, this E is the coupling constant, right. So I am just pulling that out, the electromagnetism coupling constant, okay. So that I can just think about the actual physical state, the amplitude of the actual physical state that is going on inside. What do I mean? I mean I am going to write this as, I am going to take the spin, okay, or the helicity state of the E plus E minus and take the helicity states of the mu plus mu minus and just make use of that to compute the amplitude. Basically I pulled out the coupling, the dynamics basically I pulled out, the rest of it I am going to calculate, okay. Again these are helicities. There is a way in which we can now represent the helicities and get our calculation done, okay. So there is a reason why it works out this way. Let me quickly write out why. So there is a propagator, okay. Now we did not talk about what a propagator is in quantum field theory because that is not in the scope of this course, but you can go look up what that really is. The propagator will give a term that is proportional to 1 over center of mass squared. In fact it is 1 over center of mass squared, okay, because you have a massless photon intermediate state, you will get a 1 over center of mass squared term, but then you will also have so these are all spinors, right. So in the amplitude, when you actually take a Feynman diagram and apply Feynman rules to write down the amplitude, you will get spinor currents, okay, that look like this. There is a gamma mu in the QED vertex, remember. So you will get things like this, okay, which will turn into a factor of ECM squared, okay, and basically these just cancel with each other, okay. So that worked out for us, so I am not going to really work through that part. The real fun is in what happens to the helicity states. Once the ECM square term cancels in the numerator and denominator, we can just work with the helicity states, okay. So let us see how to do that. So the problem has reduced to computing just this, right, going to S mu plus S mu minus, okay, and if you want we can just call it S1, S2, S3, S4. That is why we wrote the 1, 2, 3, 4, right, in the diagram, Feynman diagram. So that's, so it can help us to label it differently also. This is nothing but I can take the total helicity, okay, of the initial state and take the inner product of the helicity or the polarization of the photon, that is the mediator here, okay. So I am going to take that first and take the inner product with the helicity, the total helicity of the final state, which is mu plus mu minus. Okay. Then of course I have to sum over all the possibilities that the photon polarization can take. That is it actually. Okay. Do you agree? This is the total amplitude. I take all helicity combinations I can have in the initial state, and then account for all the helicity and the final state also, and account for the helicities possible in the intermediate state, which is the photon here. That helicity is what we call the photon polarization. Okay. Okay. Now we are going to do this in which frame? Of course, we are going to do it in the center of momentum frame. That is the easiest, right? So, in the center of momentum frame, I can now take the propagation to be the z direction. So, I can take this to be the z direction. Okay, if you want, I can call this the y direction and the one coming out of the board the x direction. So, I can write the momentum as, remember these are massless particles, and center of momentum means now both if they are massless, both the energies of the two initial states are the same, which means I can write the 4 momenta as simply these. Right? Agreed? This goes to the right, this goes to the left. That is all it is. Okay. Now, it turns out for this problem, it is simplest to write the helicities in the linear basis, not the circular basis. You can do it in the circular basis, but it is just easier to do it in the linear basis. Okay. So, I am going to write then that in the linear basis, S1, S2, right, this state, right, could possibly be either like this, okay. So, I am literally drawing the helicities here, okay, polarizations if you want, electron polarization if you want that term. It can be this or it can be like this, okay, or it can be like this, or finally this. So, what does this mean? The polarization has to be perpendicular to the z direction, right. So, take the first, so if it is pointing up and down, think of it as the y direction. If I am pointing it in the horizontal direction, think of it as the x direction. Okay. So, literally the polarization is perpendicular to the propagation. So, these are the 4 possibilities, right. Okay. So, I am going to wrap up with one question which we will take up in the next lecture. Among these 4 possibilities, which of these will form a spin 1 photon? Remember, these are all spin half states, right. I need to form a photon with spin 1, right. So, think of the helicities as spin also here. Which combinations would ultimately form a spin 1 photon? So, those are the combinations that we are going to pick from this, both in the initial state and the final state, and construct the amplitude. Okay. So, this we will do in the next class, and that will easily help us identify the amplitude and hence the cross section. Alright. So, I will leave you here. Thank you. See you in the next class.